Now, I've graded whatever homework ones I've received. Now, if you haven't turned yours in yet, don't feel bad because you are in the company of half the class. So only 5 out of 10 have submitted so far. So don't think that you're lagging behind the class as a whole. That said, as you look at the schedule, the due dates keep coming. So first homework had 8 problems. The next few have fewer problems. So that might give you a chance to catch up. There's one other thing I need to one thing I sometimes forget to do, unfortunately, when it comes to classes like these, it's a mixed undergraduate, graduate class, so 400, 500 level, that there is supposed to be a distinction of some kind between the work that undergraduates have to submit and graduate students. What I used to do in some classes was apply a curve, but I was told that that's not the right thing to do. There should be an actual difference in what work is done. Now, as I look at the upcoming homework assignments, what I might decide to do is say that certain problems are only required for graduate students. I haven't done that yet, but that's something that may happen in the future. But in the meantime, I'll make this adjustment. So for your Math 515, this has been the policy for everyone up to this point. But for 14, it's 2. So graduate students need to do 11 out of 12, undergraduate 10 out of 12. Then, as I mentioned, that this may happen as well. Okay.
Does that mean their exams will be different?
For what?
The final will be different?
Oh, test. There no test.
Like the final?
Yeah, we got nothing.
No, I got the final.
No, there's homework and only homework.
Great idea.
Okay.
Okay.
Sam.
I'll be thrilled about it, but when I did it last time, no one complained. But
So there's an exam, like slot, but there's no exam.
right. So don't throw up.
Okay. I feel so much better about this class.
Oh, okay.
Because I noticed on the syllabus that it mentioned nothing about the exam because either be comprehensive or not. So I'm like, I assume if there's no test, it'd be comprehensive. So then I'm like, yeah, it's gonna be comprehensive. And then I meant to ask you, and
Okay.
I liked your tests like last semester, by the way. Like your tests were better than the homework.
is it like tests or
Well, like we went over the material like in class, so that's a lot easier than the homework, which is like I thought.
Yeah.
you teach other classes? You teach other classes?
Yes, and I hope it'll take some of them. But the class he's referring to is what I taught last spring, Math 417, 517, which while it will be offered in this coming spring, I think it will not be taught by me. But that's a PDE part of the class. And what I do in that class, and often generally when I have a test, whether it's in class or take home, I create a practice test. And I put out a solution to the practice test. So there's no surprises whatsoever as to what sort of do beyond. But then it's a chance to firm things up and make sure that you're ready for the problem. So it helps the test to be more humane than it would otherwise be.
if it was a class ahead of
Yes. Right. Well, if you consider problems that, even the relatively small number of problems you've done so far, can you imagine one of those being on like a 75-minute test?
But, like, isn't it like a 2-hour slot, whatever hour slot?
2 or 2.5, it changes. I don't know.
Yes.
Yeah, but then I packed a whole special for problems, it could be 10 problems or something. You have your freak out, that there's a half hour gone.
Yeah, it's not as long as you think it is.
Yeah.
Well, my exams only got 50 minutes
Oh,
for my math test.
even finals?
Well, final, I think, got, we're supposed to get 2 hours, but we didn't get 2 hours.
Yeah.
Great.
Can you imagine, like, here, do Graham Schmidt.
Maybe that day, maybe that semester.
We're getting rolls for 2 hours. Yellow products. Or what I'm gonna cover later this week, series solutions. I put that on an in-class test, y'all hate me. Might hate me. I'm not looking forward to even covering that section, let alone what the special experience from doing the problem. Okay, so, typo. Okay, so, and I'll have to adjust this a little bit. So I just totally forgot that I need to have some sort of distinction. Sorry, graduate students, but, okay, now, into today's stuff. Still continuing with linear operators on some function space that I started covering last time. So one thing that's very helpful to do to solve certain problems is when you have any kind of linear operator, whether it's matrix, that's an operator on an ordinary vector space like Rn, or a operator on a function space, is to take a function of it. So what does it mean to take a function of a matrix? Well, I can tell you, in terms of the power series for a function, because what can you do with matrices normally? You're accustomed to adding and multiplying, performing those basic operations on them. So the whole idea of taking like an exponential of a matrix or a cosine of a matrix might seem a little strange. But what you can do is, if you want to take a function of a matrix A, and here is your function, described as a power series, like a Taylor series, for instance, for the exponential, as an example. And x naught is the center of your power series, often 0. Then here's a function of a matrix. It just involves matrix multiplication. So you take your matrix A, and notice I have minus x naught times the identity. Actually, I should make that clear here. It's the identity matrix. So all you're doing is, when you subtract the number times identity, all you're doing is you're subtracting x naught from each of the main diagonal entries of A, and then you're multiplying it with itself to raise it to the nth power. So A here is playing the role of x in your power series. So that's how you can describe a matrix exponential. And since this is probably the first time you've ever heard of a matrix function, before I talk about operators, I'll give you some examples. Actually, I deal with matrix functions quite often in my research. So suppose you have a system of linear equations. Ax equals b. If A is invertible, then the solution given by x equals f of a times b, where the function f of x is just 1 over x. Whenever we're putting it, f of a is a inverse. So, I mean, this is something you would learn from linear algebra, that to solve a system A equals b, if you compute the inverse matrix of A, then it's A inverse times B. But you can think of that as a matrix function. Reason why I don't have to worry about division by 0 in the case of f of A is A is invertible, therefore all of its eigenvalues are non-zero. Because when you take a function of a matrix, basically you're applying a function to its eigenvalues. If they're all non-zero, then it's irreducible. Second example, suppose you have a system of ordinary differential equations. Y prime is equal to AY. And let's suppose you have an initial condition. 0 equals some vector y naught. And the solution is y of t equals e to the at y naught. So here we have a matrix function. I could write that as f of a y naught. The function in this case is e to the xt. It could be the exact solution at any time t. I got one more, also comes to ODEs, and I'm going to do this one just because you might find it strange. The number system of ODEs, whereas y double prime plus ay equals 0. Because y double prime, second order system of ODEs, you need two initial conditions. So you have y of 0, the y naught, y of 0. And the other initial condition, y prime of 0 equals c naught. The solution y of t is equal to cosine a to the 1/2 t y naught plus sine t naught. So we have some rather unusual matrix functions in this case. So taking the square root of the matrix, which is a very common application of a lot of presentations about square root of the matrix, but times t, when you take the cosine of that, You can describe what this is using a Taylor series. So it works with a Taylor series for cosine itself. And then similar to this function here. I should point out though that if you were to work out the Taylor series of both of these, any powers of A would still work out to be integers. So even though it's square roots here, you don't actually need them in practice. Now this requires that matrix A be called positive definite. So it needs to be symmetric. Otherwise, the solution formula would not be valid. So if we're taking the square root, we want the result of that to give a real matrix. Also, we're got a negative exponent here, so you're taking the inverse of that. So you can't do this for a scale matrix. All right, so here's my favorite examples of matrix functions. But what we're really interested in here are not functions of matrices, but functions of linear operators on a Hilbert space. And matrix functions can help us with it. So I can describe a function of an operator the same way as I can describe a function of a matrix using a power series for a function. So f of A is equal to sum and A minus identity n. So as you see, it's identical to the definition of a matrix, a function of a matrix. Is whatever operator you have here, matrix or operator in Hilbert space, that's what you put here. Where I is the identity operator. On whatever space your operator is defined on. Now, last time I showed you how to obtain the matrix of an operator with respect to some orthogonal basis. So the matrix of a function of an operator is a function of the operator's matrix. So actually, you want to put it out in words, might be easier to put it just that way. Matrix of a function of the operator is matrix of the operator. So given a starting point of your operator, it doesn't matter whether you take the matrix first and the function or a function and the matrix. Here's an example. I mentioned matrix exponential linking to the ODE, or system of ODEs. So here we define a matrix exponential using the Maclaurin series of the exponential, in other words, the Taylor series centered at 0. And what you have to be careful about with power series, though, is you need to make sure power series converge before you use them. Now, in exponential, it's not a concern. The Lorentz series for the exponential converges for all x. So for any matrix A you use here, the series will converge. So you don't worry about that. The matrix, the exponential of an operator is defined in exactly the same way. Because we all know what it means to take a power of a matrix or power of an operator. All you're doing is you're applying the matrix or operator to a vector in your space n times. So now I'm going to focus on what are called self-adjoint operators. Now, I've mentioned operator adjoints before, and what it means for an operator to be self-adjoint, when it's equal to its own adjoint. So we're going to be revisiting self-adjointness here. Keep in mind that the synonym of self-adjoint is a Hermitian operator. So any operator whose adjoint is itself. And these are relevant in quantum mechanics. So this notation here, where we have the angle brackets that you're familiar with from scalar products, but the only thing we have in the angle brackets is the operator, but it's defined to be this scalar product. So you have some function psi. So the inner product of psi with a psi is the average value of this observable. So the Smith expression, the A in angle brackets, is called the expectation value of A. It's important that the function be normalized. And just refresh my memory what that means. That its scalar product of itself must be 1. Because otherwise you'd have to divide by the scalar product of itself. Well, as a personal comment, I find this notation rather strange because clearly the expectation value of A depends not just on A, but whatever normalized function you're using in the scalar product. But that dependence is not indicated in this notation here, so I'm not sure why we're doing that. But this is what the book's doing, so I'm going along with it. Hoping it doesn't become an issue. Okay. Now, if I take the expectation and then take its complex conjugates, that's what the star is for. So that I fill in what the expectation means, just a definition from above. But when you take the complex conjugate of a scalar product, that's the same as reversing the operands. But then I can take this A, apply to the left operand, and move it over to the right as long as I take the adjoint. That's just what I've done here comes from just from the definition of the adjoint. But A is self-adjoint. So A dagger is just A, which is the expectation value of A. So I took the complex conjugate of the expectation value, and I wound up with the expectation value. So that means it's a real number. So anytime you have a number that is equal to its own conjugate, it's real. So even if the operator A or the wave function psi is might be complex, the expectation value is still real. Sorry, I forgot to check the chat. I saw a comment from 40 minutes ago. So I'm not even sure what the context was for that. Okay, I think I know. All right. Now, before I continue, I'll refresh your memory on something about something. When you take the adjoint of an operator, the matrix of the adjoint is the adjoint of the matrix. So what that means is, if you have an operator that is self-adjoint or Hermitian, then so is its matrix. If you also have a matrix is real, that means it's equal to its own transpose. So we call it a symmetric matrix. Symmetric is mainly really meaningful for cases of a real matrix. Sometimes it does come with matrices. We actually call them complex symmetric in that case, which once in a while can be interesting. But usually when we think symmetric, we're talking about a real matrix. If it's a complex matrix, it's equal to its own Hermitian transpose, which stays Hermitian. Those are two concepts that correspond. Symmetry for real, Hermitian for complex. Okay, so as an example, here we have an operator x, and what I mean by that is, what the operator does is it takes whatever function you give as input, it just multiplies it by x. And the function space we're going to work with is called L2. So that's the space of all functions for which this integral is finite. I'm not sure why I have the word and here. Okay. I could just be more rigorous, exists and is finite. So when this integral is well defined and it's finite, then we say that the function is square integrals. Those are all the functions that are in L2. So a function f of x doesn't have to be continuous. For example, it could be piecewise continuous and still possibly be in L2. But certainly, as x goes to plus or minus infinity, f of x needs to go to 0. Otherwise, there's no way that this integral would exist. So here's our scalar product. It's just the integral of f conjugate g from minus infinity to infinity. So that the natural choice of scalar product for this space. And as I mentioned, if functions in L2, they got to go to 0 as x becomes infinite. In terms of a finite norm. So now I'm going to look at this scalar product of f with the operator x applied to g. So scalar product of f with xg. Now, writing out what that scalar product is, I'll have f conjugate and then x times g. But now I'm going to take the x and associate it with f conjugate. Now x is real, so x is equal to x conjugate, which gives me this. But then that is the scalar product of xf with g. But that's also equal to x adjoint f. Because whatever operator I have here, if I move it over to the f, that's taking the adjoint. But that's the same as if I just move x over. In other words, x is equal to its own adjoint. So x is self-adjoint or Hermitian. I guess this point is redundant. Because I also have it down here. but I'll make the comment. That's because of the definition of the adjoint. Is there any questions about what happened in this example? Yes.
Is those on the dagger, like for the X, F, G, or
Oh, wait, where?
like that? That's what's on dagger.
Right here?
Yeah.
Well, it could, but the thing is, alright. So, not because of this though, because here we just have XF. Now, this would equal this because of the definition of the adjoint. But so the point is, because we started with FXG and we wound up with both this and this, then we say, oh, X must be self-adjoint.
Was that example asking a question, or were you just saying of finding out that X?
It's all about finding out that X is self-adjoint.
That was just the implied question.
What?
That was just the implied question.
Yes.
Just gonna say it.
Okay. Yeah. Oh, yeah, I guess the mission was not really stated up here, but yeah, like, oh, here's an operator, let's just do
Oh,
something.
let's consider this.
Yeah.
There it goes.
Yeah, and yeah, I guess I explain what consider meant. Okay. All right. Well, in that case, let's do that again with another example. Okay, so now we have this operator P, also defined on space L2, and what this operator does is it takes the derivative of whatever function you're applying it to, and it also multiplies it by minus I, where I is the imaginary unit, or square root of minus 1. This is a momentum operator from quantum mechanics. So I'm not really pulling this operator out of thin air. So what we're going to do here is to find out what its adjoint is. Okay. So we start with F scalar product with operator applied to G. So here I just fill in what the definition of the operator is. Then I write out what the scalar product is. And then I use integration by parts, where F conjugate is the U, and G prime is the DV. When you have integration by parts, well, if there's a derivative in it already, that's the natural choice for DV, because then it's really easy to get V. So here we have U, V, minus integral of V du for differentiating F conjugate. But to be in L2, a function must go to 0 as x goes to plus or minus infinity. And whoops, I don't have a minus down here. Let's stop. Minus. Okay. So these terms will go away. So then I have minus I minus, so I get a positive I, scalar product with F prime of G, because it's the F prime is conjugated, so it goes on the left. But then I can switch the operand as long as I take the complex conjugate. Now, in this step, the I is not part of the conjugate. I've only taken the conjugate of a scalar product. But then if I move the I inside the conjugation, its sign must flip. So, so now I have a conjugate of a whole thing with minus I on the inside. But that's the operator P. So I can take the minus I, move it over to the F prime. This is PF. So now I have conjugate of G scalar product with PF. All right, so this is one expression that we arrive at. But the other thing I can do is if I go back to where I started, and then by the definition of the adjoint, I take P and move it over to F, and thus have to take P's adjoint. And then I take the conjugate of that, which flips the operands. Now, because I have the same starting point, these final expressions must be equal. But what's the difference between them? The only difference is in this one I have P, and this one I have the adjoint of P. It must be the same. So that's what we're doing. We're just showing operators are self-adjoint. That's what we're doing today.
Is there a reason why, like, that whenever it talks about the operator and it says like what the operator does, that it uses f of x, but it's always applied to the g in our like work example? It's just so happening.
It's just a way of running it.
Okay.
It could be written the other way. So yeah, I could have done like G scalar product PF. Any questions about what happened here? Now, next thing to do is look at the expectation value of the operator P. Oh, you know what? I just realized I need something. If I assume that scalar product of F with itself is equal to 1, I need that for this definition here. The expectation value of P is given by this scalar product. But then I write out what that is. So it's minus I times the derivative. I also need F to be real, because otherwise I would need to compute this one. But when you have F times F prime, that's equal to, and I'll add another step in here. One half times the derivative of F squared. So now we have the integral of a derivative. So we end up with just f of x squared evaluated at plus or minus infinity, but to P and L2, f of squared must go to 0 as x goes to plus or minus infinity. So we get an expectation value of 0. And that really surprised because what does that do? It takes a derivative and it multiplies by minus I. So this operator P applied to a real value function gives you a complex result. But then the expectation value has to be real. So in that sense, it's not really surprised that the expectation value of P would be 0. Any questions about this example? It's one of those good no thing seems to come up fairly often. The F times its derivative. And it's by like unwinding a chain rule, this is what you get. These are useful fairly often. Okay. I seem to have come to the end of the notes. No surprise, we have still time left over. And that means there's time for homework questions. And on any homework, like I said, if you want to ask questions on homework 1, half the class is in your boat. So okay.
What does it change with the process? Said you were calling it
Great, Schmidt.
how does that it being shifted change?
Okay.
On the very first sentence, it's shifting.
Oh, we shifted Lagrange polynomials.
Yeah, I'm just good at saying words. Euler's though, because.
Yeah.
But
Yes. Okay.
how does that change the word with it being shifted?
Oh, okay. Okay. First, let me pull up a problem. Okay, so we're dealing with this problem here. Okay, so you're asking what the significance of shifted. I guess we can refer to that bit of information as fluff. Reason why it's called shifted is that Legendre polynomials, unshifted, are orthogonal on the interval -1 to 1, whereas these are orthogonal on the interval 0 to 1. So that's the shift that's going on.
So it's shifted, but it's bolded. Or sorry, it's fluff, but it's bold.
Unfortunately, that is a thing.
So it doesn't, like if I ignore that word, it wouldn't change it. Besides the interval that it's on.
Okay, well, okay, there is something else though that does complicate matters. So the Gramsci process is going to change, but not because of bold fluff. Because of how you're supposed to scale the polynomials so that when you plug in x equals 1, you get 1. And you see that would happen with all 4 of these. Because what Gram-Schmidt does, as I described it to you, it generates a sequence of orthonormal polynomials that are not, so you would not be getting these, you'd be getting scalar multiples of them. Now, so there are 2 ways you can handle this. Number 1 is just go ahead and carry out Gram-Schmidt like before, or in every example where you generate orthonormal polynomials, and then you go back and you plug in x equal 1, see what you get, and divide by it, so that we get these. Or you can generate these as you go, where instead of doing the normalizing step in Gram-Schmidt, like you carry out this normalization, but then what you have to remember to do in the Gram-Schmidt process, okay. So right here, you would have to divide by the scalar product of phi mu with itself, because this is the correct Gram-Schmidt when the functions phi mu are orthonormal. If they're not orthonormal, it still works as long as you divide by that scalar product itself. So either way, however you want to do it.
That one sounds
Probably, yeah. Although it does kind of remind me of the boil water mathematician joke, which I will tell now. Okay, so this guy's trying to find out what job he should do, so he goes to like a career counseling center and they give him some tests. to find out what his aptitude is. So they give him a task where there's a stove, and there's a pot of water sitting on a table, and they tell him boil the water. So he takes the pot, moves it over to put it on the burner on the stove, and turns on the burner and boils the water. Okay. For second test, same situation, except the pot of water is already on the stove, and they tell him to boil the water. Well, he takes the pot, moves it to the table, then moves it back to the stove and boils the water. And so they tell him, like, well, you should be a mathematician. Like, well, why? Because you reduce the problem to a previously solved problem.
I get it.
What?
I get it. Yeah.
Yeah. Okay. And yeah, I kind of do think that waste of time. Not that degree, I hope. Yeah. Okay. Any other homework? What? Someone say something online? I thought I heard something. Are there any questions? Okay.
Number 5, how do you use the delta specific? Or yeah, is it delta in?
Oh, okay. So so all this means is you remember what this means, right?
In that one, but I don't see how it is with this one.
Okay, so this is equal to 0 if n is not equal to n, which is what you'd expect because these polynomials are supposed to be orthogonal. So where you actually use this is to make sure that these polynomials are properly normalized. In the case where m equals n, that when you take your t0 and plug it in here, you have to make sure that the value of this integral turns out to be pi. So if not, then you got to rescale. So I get really what you do is you would divide t0 by the square root of whatever you get. To make and then multiply by square root of pi to make sure that it's pi. And then similarly, but for all other ones, t1, t2, etc., then this integral should turn out to be pi over 2. So that is, and how you handle that is, I guess, like talk about the other problem where you could just rescale them at the end. Other questions? I'll back it up. I will close with one fun fact about Chebyshev polynomials. I don't recall exactly when they'll come, what discussion there'll be of them later in this course. I believe they do come up, but since they're in this homework problem, I'll just throw this in here. Okay. So a definition of a Chebyshev polynomial. I mean, you give them the first few ones, but in general, they are equal to cosine of n inverse cosine x. x, provided that x is between -1 and 1. And the reason why I think this is a fun fact, because I just think it's cool that an expression like this, which is very non-polynomial looking, is still a polynomial. And it's actually a pretty fun exercise to convince yourself of that, which you can do by considering a case, the simplest case is like n equals 0, n equals 1, and then all later iterative polynomials satisfy, well, because again, if we're talking about polynomials in general, satisfy what's called a 3-term recurrence relation. Each one depends on the previous 2. I don't know if that relation is mentioned here. No, it's not mentioned in this problem. So once you see that the first 2 are polynomials and you have a recurrence relation, then it's easy to see why the rest of them are. Now, this definition only applies for x between -1 and 1 because that's the domain of inverse cosine. But for x beyond this interval, this definition just has to be adjusted using hyperbolic cosine. Okay, I'll throw that in there because you don't know anything about traditional polynomials, it should be this. Okay, now I can finish packing up. Assuming there are no other questions from people in here or online. Okay. All right.